every single grade, and that's the story of the evolution of Wade.
BC 7-4, let's take it to a new level. We have a U shape. Maybe it's a parabola, maybe it's not, but it's some kind of curve, and we've got a couple of staggered points on that curve. Now, of course, you all remember the secant line, right? So the secant line connects any 2 points on any curve, and the slope of the secant line is, of course, y2 minus y1 over x2 minus x1, straight out of middle school, right? Very easy concept. Okay, now do you remember this is going to be a terrible approximation from the last lesson 7-3? You remember that? Remember how we used the secant slope to estimate a derivative or a tangent slope in a chart, right? But maybe it was close, maybe it wasn't close, it was just our best shot, right? But here's something we didn't mention. There is a place, somewhere, there's a point of tangency where the tangent line is exactly parallel to the secant line. Now that point of tangency probably was not the point we were picking, like estimate f prime of 4. Okay, 4 comma whatever probably was not the point where it was parallel. But this is so cool. If you think of all the infinite tangent lines, there's going to be at least one that lines up to be perfectly parallel to the secant. Now that's interesting, and that is a mathematical fact. We did not know that was true until 1797. That's how long it took to prove it beyond a shadow of a doubt, even though other mathematicians surmised it was probably true. Now I want to show you this case. See this little sharp corner right here? Yeah, good luck skiing down that ski slope. You're going to get stuck down there in the sharp valley, right? That's not going to work. But if you draw the secant between these 2 points, let's say I made these straight across. I did intend to make those straight across. So what, the slope is 0, right? So secant slope is 0. It's a horizontal line, slope 0. Is there a place on the curve where the tangent line goes parallel to that secant? Okay, well, let's see here. We've got angled. Oh, wait a minute. The tangent line's getting steeper and steeper and steeper. It never goes parallel. But Mr. Wade, you just said that if you have a secant line, there must be at least one place where the tangent line goes parallel. That is true for certain kind of curves. Do you know what's causing all the trouble in this graph right here? You know what's causing the trouble? It's the sharp point. Remember what we call those in previous lessons? It's called a cusp. A cusp is the fancy calculus term for sharp point. That's causing the trouble. If you have a sharp corner in part of your interval where you've blocked it off, there is no guarantee that your tangent line is going to eventually get parallel to the secant. This is a big deal. Seems pretty basic, right? But it's a big deal. Okay? But what if I were to block this off on a window from the cusp to some other place over here, let's say? Okay? So let's say from the sharp corner over to maybe this random place right here. All right. Look at the blue curve now. Let's look at this close up. Would there be a place between the two endpoints, the cusp and then this black dot up here, where the tangent line to the blue curve would eventually go parallel? Oh, it's going to happen like right in there, maybe somewhere. It will happen. So it's okay if the cusp is an endpoint. It's okay if you have an interval where there's no cusp at all. But you can't have the cusp within the interval, or that whole theory that I just proposed over here completely fails. All right, so this discovery was made in 1797. By, who's this guy? Have we talked about Lagrange before? Maybe once, maybe not. Joseph Louis Lagrange, French mathematician, of course, with a last name like Lagrange. He is ranked number 5. Whoa, I don't think we've talked about this guy before. He's in the top 5 all time. And cool fact about him, by the way, you remember number 1 ranked Euler, right? I guess this isn't long enough to do a history break, but Euler, number 1 greatest mathematician ever, he gave a PhD to Lagrange. How about that? Euler was his PhD consultant in mathematics. Talk about having a great professor to work under. So he was a protege of Euler. And then, really cool, Lagrange actually gave out multiple PhDs. Once you get a math PhD, you're allowed to hand out PhDs. Well, Lagrange gave out multiple PhDs, one of which was to number 63 ranked Fourier, another French mathematician, all right? Why is Fourier important? Fourier founded the field of mathematics called Fourier analysis, which is very important in modern technology. And my father, who eventually came along in the 1900s, my father ended up being the world expert in Fourier analysis. And he took that field way beyond what Joseph Fourier ever planned, but he really pioneered that field. So my dad, he's always thought that Fourier was one of his favorite mathematicians because, of course, he was pioneering that field. So kind of cool connection there. All right, let's fill in some more blanks. So we call this the mean value theorem. All right, we just abbreviated MVT in calculus classes for slang, but mean value theorem, mean means between, all right? So at some point between, not halfway necessarily, but at some point between the other 2 points, the tangent will be parallel to the secant. Okay, let's see if we can state that. But if the curve is blank, so let's go back and talk about the failure, which was when the cusp was included. Does everybody remember that the cusp is one of the 3 types of non-differentiability? Anybody remember this? This is the single longest vocabulary word you will ever get in any high school math class right here. Non-differentiability, all right? In other words, derivative does not exist. That's an easier way to say it. Okay, so the cusp was one of the 3 ways, a sharp corner. You can't draw a tangent at a sharp corner. Non-differentiable, derivative fails, tangent slope fails. Another place was when we said the vertical tangent. You remember that? When you go like on the side of a circle, on the side of a circle, the tangent line goes vertical, and you learned in middle school that a vertical tangent line or a vertical line has no slope, undefined slope, which means the derivative is undefined. And then number 3 is if the curve is just D and E. Vertical asymptotes, holes, jumps, all 3 of those, right? If the curve doesn't exist, then how could the derivative exist, right? Okay, so you've got to avoid cusps because we showed up there that it didn't work very well. You also have to avoid vertical tangents and does not exist. Well, guess what? As long as the curve is, let's cover up non-differentiable, right? As long as the derivative exists, you're okay. You just got to watch out for those cusps and vertical tangents and stuff. So if the curve is differentiable, and by the way, every single theorem we learn this year in calculus, pretty much the blank is if the curve is continuous, all these theorems work. This is the only theorem in calculus that we study in Calc 1, Calc 2, where it has to be also differentiable, not just continuous, but also differentiable. The derivative has to exist as well, okay? Only time you'll see that. On the open interval from A to B, why the open interval? Okay, remember we said that if you block the interval off right at the cusp, then the whole mean value theorem will actually work and you'll get a parallel tangent line? Okay, that's only if you make it open circle, an open interval in parentheses, not square brackets. Because if you include the cusp, which would be like moving this line like a millimeter that way, if you include the cusp, the whole thing fails. Okay? So you've got to exclude the cusp, but then go between those 2 basically. So that's why it's an open interval. All right. Then there will be a guaranteed x value, which is the point of tangency, by the way. And we normally call that x comma f of x. In the mean value theorem, it's the only time that we'll call it c comma f of c. All right, so that is merely the point of tangency is all that is right there, okay? All right, so there's going to be some x value, but you're going to call it c. So that c is between the 2 endpoints, okay? A, B, somewhere between. I'm trying to interpret for you from English into calculus, or really like calculus English into plain English is really what this is. There is one place where the tangent slope at x equals c, like that, is parallel to or equivalent or equal in slope to the secant slope from A to B, because the secant slope needs 2 points to anchor it, right? And then the tangent line only needs 1 point of tangency to anchor it, okay? So that's all that's saying right there. So for example A, we've got the mean value theorem is going to be satisfied for y equals x minus x cubed on the specific interval from -1 to 2 at what value of c, which is really what value of x. It's really like, you know, what x coordinate of the point of tangency would you get? It's just this one problem where they call it c instead of x. It's not a big deal. All right? So here's what we do. First thing I would probably do is remember that an interval is never xy. It's always xx. That's x1, that's x2. Those are your anchors. Those are your endpoints for your secant line, okay? What I would probably do first is just go ahead and plug each of those into the equation and figure out what the y coordinates are. It's a great place to start. All right, so y equals x minus x cubed. So that's going to be -1 minus -1 cubed from that number right there, okay? And then that would give you -1. -1 cubed is -1 times negative last is +1. Okay, so when I plug in -1, I come out with 0. Hey, isn't that the point, -1 comma 0? Now go to the graph I've drawn for you. You won't have to do the graph in the future, but I really want to show you a visual today as to what's happening, especially for you visual learners. -1, 0 is one of the anchors. That's going to be one of our endpoints, okay? And it's already on the graph for you. But in the future, you won't even need the graph. Okay, take 2. Plug that in for x. 2 minus 2 cubed is 2 minus 8, which is -6. Okay, so the other endpoint is 2, -6. All right, let's go to the graph. Right 2, down 6. Oh, it's down here somewhere. Okay, let's draw a secant line. So between this point and that point, we're going to get a dashed line. So we've got our secant line from -1, 0 to 2, -6. Okay, what does the mean value theorem say? Well, it says that the secant slope shall match or be parallel to the tangent slope at least once. If not, we only saw once over here, if not twice or 3 times or 4 times. You could have 4 parallel tangent lines to one thing. There are some crazy curves we will study at the very end of the year where you have infinite parallel tangent lines in a small finite space. Let that blow your mind for a second, okay? Infinite tangent lines in a finite space, whoa, okay. We'll get to that later. All right, so here we go. Shouldn't we find the secant slope? Since we've got the dashed line over there. Might as well find the secant slope. Well, that's y2 minus y1 over x2 minus x1. Okay, y2 -6 minus y1 0 over x2 2 minus x1 -1. -6 over 2 plus 1 is 3. I'm coming straight out of middle school, right? -2 is your secant slope. Now, where is the mean value theorem satisfied for the curve x minus x cubed, which I've graphed over here? When the tangent line matches the secant line's slope. When the two slopes match. Well, Mr. Wade, I know how to get a secant slope, middle school. How do I get a tangent slope? Oh yeah, we've been doing it all year. Derivative. Tangent slope. All right? Not a specific number, but a formula. What is the formula for all the possible tangent slopes? The derivative is the formula for all the possible ones. Y prime, derivative of x is 1. Derivative of x cubed is 3x squared. Keep going. All right. 1 minus 3x squared. That is every possible tangent slope. Could one of those be parallel to -2? The mean value theorem says guaranteed. As long as it's differentiable. Oh, it's a polynomial. Polynomials are always smooth. Polynomials don't have cusps. All right? They're too basic and too ordinary to have cusps. So guess what? It's a smooth function. It is differentiable, all right? No sideways vertical tangents, no D&Es, no cusps. So kind of look at this. Here comes the curve, and I'm on the roller coaster, and over here, somewhere I think I'm going to end up being parallel. It almost looks like it's at 1. Of course, it could be 1.1, and we can't tell with the human eye. But somewhere there's a parallel tangent line. We need to find it. I wonder how we would find that place though. Wait a minute. When two things are parallel back in the integrated classes, don't they have equal slopes? If that's the tangent slope formula, and that's the real secant slope, wouldn't they just be equal to each other and that would make them parallel? It's so simple, right? Tangent slope shall equal secant slope somewhere. And Mr. Wade doesn't like his x squareds to be negative. I want my x squareds to be positive. Isn't that the proper way to solve things? So we're going to add u to the other side and make u positive. And at the same time, because you're all smart, you can add the two back over this way. All right? So that gets rid of that one, and in one step, you've got 3 equals 3x squared. Oh, wait a minute. Divide both sides by 3. That's going to be 1. That's going to be x squared. And you get x equals 2 answers. Anybody see it? X equals plus or minus 1. Oh, so I was right about that 1. I was just guessing. But we got another friend here, negative 1. Okay. So the tangent line at x equals 1 should be parallel. This is pretty much, I tried to draw this to scale for you too, so you can really see it. We don't draw a lot of stuff to scale often because it doesn't matter, but it matters here. Isn't the tangent line at, careful now, at 1 going to be pretty much parallel, close enough, to the secant? Okay, well, you may not trust my sloppy drawing, but you can trust the mathematics. Yes, it is exactly parallel at x equals 1. Okay? And also at x equals negative 1. So when I go to the tangent line at negative 1 right here, it is also parallel. Uh-oh. Wait a minute. This is not good. If I continue drawing that line, that tangent line, it's going to end up right on top of the secant. Uh-oh, what happened? Wait a minute, that can't be true, right? If I draw a line on top of another line, would they have the same slope? Well, yeah, no joke. They're the same line. Of course they have the same slope. But would they be parallel? No. Parallel is separate but same slope. You can't be parallel to yourself. I'm about to get overlap and get parallel to myself. That's impossible. Okay, here is the twist of the mean value theorem. Okay? The parallel tangent line must happen between the two endpoints, not at one of the endpoints. Wait a minute, we already said it. I just didn't really discuss it that much yet. Didn't I say something about the open interval over here was part of the definition? Okay, the open interval is to protect you against cusps, but it's also for something else. The open interval is to eliminate endpoints as a potential answer. Because the reason the tangent line at that endpoint matches the secant slope is because the tangent line is the secant line. All right? No wonder they're the same. So yes, you cannot be parallel to yourself. So the reason we have open interval in the mean value theorem is to eliminate the endpoints so that doesn't happen, and then you won't have a line being over top of itself. But see, you're not going to have a graph, so you won't be able to see this. So that's why you need to trust the open interval part of it. So never use one of your endpoints for a final answer in the mean value theorem, ever, because you'll get the overlap. If I had come out with positive 2, I couldn't use that one either. And by the way, you have to be inside the interval. Doesn't it say between A and B? So if you get an answer like 7, well, that's like way outside of negative 1 to 2, so you definitely wouldn't use that one. It must be between negative 1 and 2. Even though, yes, they're going to give you brackets to block it off. So they give you brackets, but you still have to answer on parentheses between, okay? No overlap allowed. So, positive 1, is that between negative 1 and 2? Valid answer, yes. 1 is one of your answers. You remember we said we don't call it X, we call it C. That's just a thing they developed in the 1700s, and we've done it ever since. Just go with it. Don't put X equals 1, say C equals 1, play the game. Okay? Negative 1, oops, endpoint, can't use it. Okay? That, my friends, is the mean value theorem. Letter B. Oh, we've got another table, don't we? Okay, very important for the free response questions. Can you read a table? All right. Now, what's in this table, Mr. Wade? Well, you know I love the real life problems. May the 2nd, 2010, in your lifetime, you know what happened. It was the 2010 flood that was the biggest disaster in Nashville history that we know of. All right. This was what we now refer to as the 1,000-year flood, because the probability of it happening is only once every 1,000 years. Okay. You lived through it. So here was the problem. We had 7.25 inches of rain just on May the 2nd, 2010, which was a Sunday, which was the rainiest day in the history of Nashville, ranked number 1. Here's the shocking part. In just 12 hours, we had 7.2 of those inches, which is what's detailed in the chart up here. Okay? Here's what made it even worse. We could have survived 7.25 inches of rain in one day, even though it was the rainiest day we've ever seen in Nashville history. The problem was the previous day, which was a Saturday, saw 6.6 inches of rain that evening, which is in the top 5 rainiest days in Nashville, followed by the Sunday that was number 1. So you have 2 of the top 5 rainiest days back to back, and the ground's already saturated, and the rivers are already up, and then this just made it worse. And houses were underwater all across Nashville. All right, I have a story about that, actually, about my house, but that's for another day. Okay, so R is differentiable. We'll get back to that. It has to be differentiable to do this problem. T is hours after 6 a.m. And so 0 is right at 6 a.m. 3 is 3 hours later. So that would be 9 a.m. 6 is 6 hours later. So that would be noon. Okay? R is cumulative inches of rain. Does everybody understand what cumulative means? That means kind of a running total, a running tab, right? So when we say after 12 hours, we don't mean in the 12th hour we had 7.2 inches of rain just in that 1 hour. No, that's like the cumulative total of the whole list, right? Okay, so what will they ask you on the AP test? At 1 o'clock p.m., what was the rate? And give us the correct units. Okay, my calculus students, you need to kick into gear because I have trained you like soldiers. You see the word rate, immediately you think derivative. Rate is derivative. R prime of 1, no, don't be silly. 6 a.m. was times 0. So you have to figure out how far past 6 a.m. is 1 p.m. All right, wouldn't that be 7 hours? So we're looking for R prime of 7. All right, is R prime in the table? No, those are a bunch of R's. Okay, so we need a derivative. We don't have an equation to take the derivative of. Well, 7 does conspicuously fall between 6 and 9 on the table. I mean, maybe it has something to do with that. T equals 7, 1 p.m. Oh, wait a minute. Does anybody know what our new favorite game is in this chapter? This is going to be a terrible approximation, right? But we're going to use the secant slope to get a very rough approximation. Now, this is not the mean value theorem where it's exactly matching. It's just kind of close. All right, R prime of 7, well, we can just do y2 minus y1 over x2 minus x1 with the neighboring points. It's all we have, and it'll give us a decent estimate. So 6.8 minus 5.5 over 9 minus 6. Okay, and let's see, that's going to be 1.3 over 3. On a free response question, actually, they would take that answer, even though you're never supposed to leave a decimal in a fraction. But they would actually take that answer because it's equivalent to the correct answer. Now, if you want to play our old favorite game called Scoot, remember, you can scoot the decimal and call it 13. You can scoot the invisible decimal and make it 30. And I like 1330 is better. It makes me feel better. But if I were on the FRQ on the AP exam trying to save time, I'd probably just put 1.3 over 3 and run. Don't actually run out of the room. Okay, use the correct units. Even though we did a secant slope, we were approximating the derivative. And derivatives are basically dy over dx, aren't they? Okay, in this case, it's actually dr over dt. Okay, but just kind of think of it as a rise over run, because rise over run is intimately connected to the derivative indeed. So either one. So remember, for your units, just say r over t or y over x. The y was cumulative inches, so cumulative inches, let me abbreviate it, per per, T is hours. You actually don't have to say after 6 a.m. Just say cumulative inches per hour, or per hours. I guess you could just put per hour, singular. And the AP graders will kill your grade if you don't put units, so you better put units, okay? Now, let me show you a new kind of FRQ question we have not covered yet, but now we're able to cover it. Is there a time during this infamous Nashville flood between 3 and 6, I put it in interval notation because it's easier, but you can look at your notes there, it's in inequality notation. Is there a time between 3 and 6, which would be what, 9 a.m. to noon, where R prime, the rate of rain falling, matched 1.5 inches per hour? Did it get that bad? We have mathematical evidence to prove that it did, okay? First of all, 3 to 6, let's go up here to the table. 3 to 6 is this interval right here. If you went from 1 inch of rain on the ground to 5.5 inches of total rain on the ground in 3 hours, can we verify that the rate of rainfall had to match 1.5 inches per hour? If not worse, at least match it. Yes. R prime is always the tangent slope. It's also always the velocity and other things like that, right? The rate. But it is definitely the tangent slope. Okay, so let's start thinking about this. Is there a place where the tangent slope equals 1.5? Is anybody's brain turning out there who's watching this? Wait a minute, Mr. Wade, seems like we just talked about this on the other board. The tangent slope shall equal a certain number at a certain place in time. The 1.5 is kind of like the secant slope. Yes, my friends, this is a mean value theorem problem, all right? I swear I just heard a dog bark. But I'm here all by myself at like 8 o'clock at night and when nobody else is here on a Friday night. Who knows? Anyway, all right. So here's what you do. 3, 1, 6, 5.5. Find the secant slope, which we'll call M. There's no accident that they picked 1.5. That is not random. I picked that on purpose. They'll pick it on purpose. This is not random. It's a dead giveaway. If it looks random, it's not. 5.5, y2, minus y1, which is 1, over x2 minus x1, 6 minus 3, our interval, gives you 4.5 over 3. And 4.5 divided into 3 sections would be 1.5. Or 45 divided by 3 is 15. Now just put the decimal back in. It's exactly 1.5. Okay, if the secant slope is 1.5 between those two, then at some point on the curve, the tangent must go parallel to the secant. The tangent line is the derivative, is the rate that the rain's coming down, and it must match the 1.5. It's a mean value theorem, okay? Now, they're gonna put in that word justify, all right? You've gotta tackle that word justify. They want you to write a clear, concise sentence in English. So please use your writing skills, even if they're iffy. Write me something nice here, okay? They want you to see on the exam. They want to see in your work that you wrote this phrase somewhere. By the MVT, the mean value theorem. See, when you quote that, you're getting a lot of points and a lot of good grace with the graders, okay? By the mean value theorem. What had to happen with the mean value theorem? Continuous? Does it just have to be continuous? No, remember, this is the one theorem where it has to be differentiable. Oh, up here they said R was differentiable. I put that in there on purpose. They will too. So we do know the curve is differentiable. By the mean value theorem, since capital R is differentiable, and you can abbreviate, that's fine, the R prime, let's just say R prime of t, must equal 1.5 on, did we say mean value theorem today was open interval or closed interval? Didn't we say open? So you change their brackets to open 3 to 6. Somewhere between time 3 and time 6, or 9 a.m. and noon, The rate of rainfall had to be 1.5. And in fact, we know from records it was actually a lot worse than that at some points too. That's the phrase. Okay, can you get all that in there? And remember, it doesn't have to be exactly this. I'm just giving you the shortest, most concise way to write it. Put the MVT in there somewhere, claim that it's differentiable, claim the open interval, and then just state this. Now, is it okay to just state that? Yeah, because your work's going to be next to it on the AP test. And I'm going to see your work on the test that you've actually done a secant slope. You can't just put 1.5 without showing the y2 minus y1 over x2 minus x1. Okay? So that'll be there too. Perfect. Beautiful. All right. Is there a time from 3 to 6 where r of t equals 2, not the derivative, but just the amount of rain? Original function is amount, right? Is there a time where the amount of rain on the ground was 2 from 3 to 6? Well, let's see. At time 3, we only had 1 inch of rain on the ground. It wasn't too bad actually at that point. But by noon, we had gained that much, so we were at 5.5 for the day. This is plus the 6.6 the previous day, right? So is there a time where there were 2 inches on the ground? Yeah, duh. I mean, you can't go from 1 to 5.5 without passing 2, right? Let's say you're on the beach. Let's say you're at sea level, which is 0 feet above sea level, right? Here's the ocean. And you walk up the embankment back up to your car in the parking lot. Mr. Wade, you should have been an art teacher here. All right? So here you are down here at 0 feet above sea level, right? You're at sea level. You start walking and eventually you get 1 foot above sea level. Eventually you get up to your car, let's say that's 5.5 feet above sea level. Don't you have to cross 2 somewhere? I don't think anybody can teleport and just appear in their car. I wish we could. I'd like to just teleport to Paris right now and go on vacation. All right, sneak past the COVID-19 restrictions. So guess what? You must pass 2. You must pass 3. You must pass 3.12. You must pass 3.2. You must pass 5.426. You've got to pass every number between 1 and 5.5. I'm trying to jog your memory here. What is this telling us? What did we do the other day? The intermediate value theorem. If you have a point above and below the x-axis and it's continuous, you must cross the x-axis. Well, guess what? It does not just work for the x-axis. It works for any interval. If you're at 1 and then later you're at 5.5, whether it's elevation above sea level or rainfall on the ground, you've got to cross 2 somewhere because it's intermediate, it's between, okay? By the intermediate value theorem, okay? So the answer is yes. By the IVT, that's our abbreviation, by the intermediate value theorem. Does R have to be differentiable? No, that's only the mean value theorem. Every other theorem in calculus, it merely has to be continuous, okay? Since R is continuous, wait a minute, do we know R is continuous? I don't think I've ever told you about this. Well, maybe a long time ago. R is differentiable. It didn't say it was continuous. Oh, this is something every calculus student needs to know. If a curve is differentiable, doesn't that mean that R is continuous and R prime is continuous? You remember this? We have kind of talked about that before. R must be continuous with no holes, no asymptotes, vertical asymptotes, no jumps. R prime is continuous. Okay. This is the thing we've never explicitly said in class, though. If you are differentiable, that implies that you are continuous, of course. Otherwise, if you had some kind of does not exist, it would have messed up the differentiability. Now, if a curve is continuous, it might have a cusp in it. So if you're continuous, you are not necessarily differentiable. That is not true. But anything that's differentiable is automatically continuous. Because these two things are true, so the original function is continuous, okay? I want every calculus student to know that this is true, but this is false, unless you put a slash through it. Now it's true, okay? So since R is continuous, which comes from differentiable, yes, all right, comma, and, add this in here, and R of 3 is 1 in the chart, so R of 3 is 1, and R of 6 is 5.5, so you're kind of stating the obvious, but they want you to get IVT in there and know what it is. They want you to state that it's continuous, but differentiable for mean value theorem. And then they want you to say R of 3 was 1, R of 6 was 5.5. Well, somewhere in between it's got to cross. right? So, or maybe then, or thus, therefore, ergo, whatever you want to use, okay? Then, R of t must equal 2 for some t that is between what, 3 and 6? So let's say 3 and 6. So some t between 3 and 6 makes it true. You're basically just stating the obvious, just kind of know what to write. And I don't care how you phrase it, you can phrase it any way you want to phrase it. Make sure you quote intermediate value theorem, continuous, give me the endpoints, and then just kind of state the obvious. Okay, that's it. So that's what you have to do on the AP exam in the free response section. That's how to play the game. All right, next question.